All right, welcome to another week of our online lab here for the 1212 lab in North Georgia. As you can probably already tell here, this week's a little bit different than normal. We're not doing kind of an actual new hands-on experiment. This week we're actually going to be taking a look really more at kind of the data analysis side and how it applies to what we call chemical kinetics, which really is going to look at speeds of reactions. You've probably got a lot of background information with the pre-lab video, so I'm not going to try and rehash too much of that. Instead, what I want to do is do kind of a quick review of the experiment. For those that haven't done the Beer's Law experiment, I think if you're taking this in the summer, some of the sections might not have done this one. Hopefully in the normal semesters, then this is a lab we typically do now for 1212. And really what that lab entails, I'm just going to give you kind of a very quick overview of it and some quick visual images and kind of some numbers to think about. And then I'll get into the actual data analysis for this experiment. But the experiment that's basically being done, that all of the data you're going to see in the Excel spreadsheet we go over is going to come from, is looking at a reaction between crystal violet and sodium hydroxide. And crystal violet, it is a dye. It's a chemical dye. It has a very dark, intense purple color, kind of like its name suggests. But what happens is if you react crystal violet with sodium hydroxide, the kind of ensuing acid-base reaction that happens will actually cause the crystal violet dye to lose its color. So what this allows us to do is if we do a reaction when we have excess of the sodium hydroxide, so we can eventually react all the crystal violet away, we should have a solution that can go from an extremely intense color to basically clear. I'm going to have some kind of images, kind of still images that I'll show you here in a second to kind of back that up. And the thing is that's kind of neat about this reaction is we can kind of track its progress visually. You can do this, just qualitatively by looking at it in the images I'm about to show, but also quantitatively through something called absorbance that I'll talk a little bit about here as we go as well. And you'll see some numerical values for it in some of the images I'm about to show. And so most of these reactions are done on a very small scale for this experiment as far as where all the data is coming from. We use these little small kind of plastic, what we call cuvettes, to actually do our reaction in, where basically we just have our solution in this little plastic. It's kind of almost like a kind of rectangular prismatic prism, if you will, kind of for its general shape. And then we kind of fill our solution in here. But the nice thing about this is we can actually put this in an instrument that I'll show here in a moment that will actually measure what we call absorbance, which effectively, if you're trying to figure like, well, what exactly is absorbance? It's a measure of how much light this solution actually absorbs at a particular wavelength. And what happens is, if we have a compound that's a fairly intense purple color like this, it's probably going to absorb light at kind of a different part of the visible spectrum, kind of really the complementary color in a way. And so for this particular one, you'll see it absorb around like 590 nanometers, I think is where we measure this particular absorbance value at. But we see some absorbance value of 1.493. Absorbance values between 1 and 2 are on the higher end. And basically, the higher your absorbance value, the more light your solution is absorbing. And it turns out, as we'll talk about kind of as I go through some of these images and kind of some of our data here in a little bit, this absorbance is related to concentration. And that'll be a big important feature of a lot of what we'll be doing as we go through the calculations for this week's experiment. And really more the data workup that we'll be going through this week. But what I want to show here is just kind of a progression of images, right? The first image we saw a second ago was after 30 seconds. Absorbance value is a little over 1.4. After 2 minutes, we see our absorbance has gone down, and we see the color that go back and forth. It's lightened a little bit. I know I'm not not the world's best photographer, so I apologize if you have to kind of bounce back and forth between these images a little bit. That's okay. We do see it start to lighten in color, but as I kind of progressively go through, you're seeing, okay, it's getting a little bit lighter yet after 4 minutes. I do apologize, the cuvette got turned 90 degrees. It's the same cuvette, it's the same reaction. But we see its absorbance down to 0.626, and we see that number continuing to decrease over time as our solution gets lighter and lighter. And eventually, if we go all the way to 10 minutes, we see our solution is pretty much clear. So I'm going to kind of quickly progress through all these one more time. If we start, there's our starting solution. And over time, we see that solution lighten in color over and over and over. So after 10 minutes, it's basically clear in this case. We see our absorbance getting very close to zero now. So what we're kind of taking away from this and what we're really wanting to look at is we can measure, and this is actually the setup for measuring absorbance. So here's that cuvette that you just saw in all those previous images, and that's why I got twisted kind of partway through as I was kind of taking it out, making measurements, taking pictures back and forth. And what we can do is we can use something called a spectrophotometer, or in this case, this is the SpectraVis Plus that you see there. And what the spectrophotometer does is it takes light and shines it through your sample, and it measures how much light gets through. And the more light that gets through, the lower the absorbance, and the less light that gets through, then the higher the absorbance. And what happens for color or for compounds that have very intense color, like crystal violet, you can actually relate this absorbance to concentration through something called Beer's law, which, like I said, if you've done that experiment, basically those two things are linearly related. As concentration goes up, so does absorbance, and the fact they go by the same multiple. Like if concentration doubles, so does absorbance. The nice feature about kind of that relationship is that everything we do this week, we can actually just use the absorbance to do all of our calculations. We don't have to worry about using concentration really for anything because the relationships we're looking at and how things are changing are really more about kind of ratio changes. And so since absorbance will change by the same ratio concentration will, we can actually just use absorbance instead, and everything will come out the exact same as far as our final kinetics-based results. Now, a couple things I do want to point out here from the data that we can kind of carry over into the first part of the kind of data analysis we're going to be looking at for our kinetics lab is that as we look at the absorbance values that are here, we actually see that it's not a constant decrease, right? Even though these time intervals like 2 to 4 to 6 to 8 minutes, like it's 2 minutes each time, we don't see the same exact change, right? The changes are actually getting smaller. That's important to note because that actually gives us information about the kinetics of our reaction in terms of whether it's a 0th order, first order, or second order reaction. And so that'll be kind of the next piece here that we're actually going to be moving into, which is I'm actually going to kind of pull up the Excel file first of data that everyone should have access to. It should be available on D2L. When you open your folder for kinetics, you'll see this Excel file in there, probably right under the lab demonstration video. And so I'm going to go ahead and pull that Excel file up right now. So we have kinetics data here that we're going to see. Everyone's file should look pretty much exactly like what I have here. And I'm just going to very kind of briefly tell you all the different pieces. For the first part of things that we're going to be doing, we're only going to be looking at experiment 1. And then we'll be kind of including some of these other experiments as well, because they're all going to have kind of a purpose as we go through and look at things. But you see basically you have time data and absorbance data, and very similar to kind of what I was just showing a second ago, we see our absorbance constantly decreasing for all of these. Only our time here is in seconds instead of kind of the minutes I had, and so we see the changes not quite as drastic as maybe what I had in my previous plot. But the same general trend is going to apply. And what we're going to be doing for the first part of this kinetics lab is actually trying to figure out what is the reaction order of the crystal violet that was in that reaction. So we said before, if I go back to that image for just a brief second here, that this reaction and kind of looking at the colors that we saw, it was all a reaction between our crystal violet dye and sodium hydroxide. Well, we used excess sodium hydroxide, and in fact, if you look at the experimental procedures given to you in the reading for the kinetics lab, we actually use a huge excess of sodium hydroxide, which is done for a particular reason. And it's basically so that if we monitor the absorbance of our solution, we are really monitoring this crystal violet dye concentration in particular. And if the hydroxide concentration is so big, it effectively just stays constant. It doesn't change, because if this concentration is, say, like 5 or 6 orders of magnitude bigger than the crystal violet, as our crystal violet reacts away, the sodium hydroxide concentration effectively isn't changing unless we have tons of significant digits, which probably isn't very realistic. And what that lets us do is basically use our absorbance data to figure out a reaction order for our crystal violet dye. And so that's kind of our starting point, is we want to figure out, is crystal violet in this reaction a 0th, first, or second order reactant in terms of how its concentration is going to affect our reaction rate. So how do we go about actually figuring that out? Well, from a data standpoint, what we're going to be doing is actually generating some plots. So if you think about kinetics and have gotten a chance to talk about kinetics, particularly in your lectures, one of the things you'll find out about kinetics is that you have these integrated rate laws, right? And you have integrated rate laws for like 0th, first, and second order. Like 0th order, you find that your concentration and time have just a linear relationship to each other. But if you look at first and second order, you don't. Like first order is a natural log relationship. Second order is then a 1 over concentration relationship to how it changes with time. And what it kind of comes from this is we can actually make a couple plots. And so the plots we're actually going to make, we're going to use experiment 1 for all of these plots. And to kind of be able to make them, I'm actually going to give myself a little bit of room. So the first thing I'm actually going to do is kind of just slide this set of data over a little bit for experiment 2 and put it with some of our other experiments. And what I want to do is kind of show you guys not just how to make some of these plots, but also some features for Excel. Microsoft Excel is an incredibly powerful tool that's extremely useful for all sorts of applications. And if you've never gotten to use it, I want to try and use this lab as a little bit of an introduction to some of the nice features of Excel that can really make your life a lot easier when you have to use it, or when, in situations where it might be useful to use it. So as a first demonstration of this, we're going to want to make 3 plots. We want one that's going to be just basically, our time and concentration. So basically concentration on our y-axis and time on our x-axis as a plot. We also want to make a couple additional plots. I'm going to just copy the time here a couple times to get things kind of generally set up. And instead of, for my second plot, instead of having absorbance, I want actually the natural log of absorbance. So I'm going to label it just like that for now. And the last one, I want 1 over the absorbance. Now, one of the great features about Excel is that instead of having to pull out a calculator and calculate the natural log of every one of these values and then fill them into these columns, which would take forever to do, and this isn't even a really big data set compared to things you might be doing, in the future, you can use Excel to make this much easier of a conversion for you. And so what we're going to do is in this box here, where I want the natural log of these absorbance values, if I hit equals and then type ln for natural log and put my parentheses, if I click the cell that's in line with basically right here, and then close my parentheses and hit enter, it'll automatically calculate the natural log for me. Now, the extra nice part about this, if I go back and highlight that cell, if I hover over the bottom right corner, I'm going to see my normal kind of looking plus sign switch to a black crosshair. When that happens, I can do this one of 2 ways. If I don't have anything down farther below, I can just actually double click. And for the data set, it'll actually fill all of them basically performing that same exact calculation. So this value should be the natural log of this one. If I come down here, like this value should be the natural log of that value. And they're all in line and calculated appropriately in that way. And so that makes, instead of doing, what would this have been, like 30 some calculations and having to do each of them individually, I did the calculation one time effectively when I entered it in this, first box, and was then able to instantly copy it and have it do all the other calculations for me. So that's a really, really useful thing to be able to kind of know how to do in Excel, and it makes life much, much easier. So I'll show that one more time as I set up the information I want for my third plot, which will actually be involving time and 1 over concentration. And so, again, if I want to kind of make this plot quickly, I'll hit equals. And if you put equals at the start of any box, it basically tells Excel you're doing a calculation. So I want it to calculate something numerically. So now I can hit 1 divided by, and the absorbance value is over here. I'm just going to go click that box. And alternatively, you could actually enter the cell kind of label. Like, see how the label is B4 that's kind of highlighted and popped up there? I could just type B4. That would also be fine. But you can also just click the box. And now if I hit enter, it's immediately going to calculate 1 divided by that absorbance value. And if, again, I want to copy all of my data, it's really easy. If I just come to that bottom right-hand corner, I see the little black crosshair, double click, and it's already calculated all of those values for me. I don't have to do anything else. Now, what am I doing with this data? Well, I said I wanted to make a couple different plots, and the purpose of this is to figure out, what's the reaction order of our crystal violet in this reaction. So to make my 3 plots, I'm going to go ahead and just make all 3 of them first. So I can just highlight my data here for my first one. I'm going to tell it that I want to insert. I'm going to want to insert a chart. And some of your headings as far as where things are here might be a little bit different. I'm doing this on a Mac, for instance, right now. If you have a PC, it might be slightly different. If you have a different version of Excel, it might be slightly different. But there should be some options to insert a chart. I always like to do inserting scatter plots in particular. So for me, that's right here. Sometimes you have to hit recommended charts and pull down and select scatter plot from a selection. So here I want a scatter plot with nothing connected. There's my scatter plot. Now what I want to do is add some things to this, right? So I want to be able to kind of modify this thing and add some different pieces of information. And there should be some different options to kind of do that. So up here I can like change chart types and different things like this. Over here up in the top left, I have add chart element. So I can add axes, I can add axes titles, which is something I actually do want to go ahead and do. So I'm going to put both my axes are going to give them titles so that I can label things appropriately. And I also have a chart title that's already there for me to edit. So first thing I'm going to do is I'm going to give this an appropriate title. And I'm going to call this what it effectively is. It's an absorbance versus time plot. I'm just going to leave it like that, absorbance versus time. On my axes here for my vertical axes, which effectively correlates to my y-axis, right? This is my absorbance value. And if there were units to whatever's on that axis, you'd probably want to put the units. Absorbance is typically a unitless measurement, so I'm not going to list any units with it. I'm just going to write absorbance. And then for my horizontal axis, we said this is time, and it's in units of seconds. I can type. There we go. All right. So now I have a plot that has absorbance versus time on it. And what I'm really looking for here and kind of our purpose for making these plots, in order for our reaction to kind of fit one of these reaction order types, we expect to see a linear plot for these things that we're making. So absorbance versus time, if this plot were linear, I would expect a 0th order reaction. Well, this plot's very clearly not linear, right? It's a curve, pretty defined curve. So we know from this plot, our reaction is not 0th order. So I can kind of set this aside. CSC Pub is going to want this plot regardless. So make sure you do have your kind of different labels and pieces on here. Keep those because, like I said, CSC Pub is going to ask for it. But now I'm going to go ahead and make my second plot. So same thing, I'm just going to highlight now. This is going to be natural log of absorbance versus time instead of just absorbance. And we can compare how that looks. So for this one, same thing, I'm going to make a scatter plot. I'm going to add my different chart elements that I wanted with my axes titles. I'll add both of them. And this time, notice I actually do have a pretty straight looking line. So I have time again on my x-axis and seconds here that I'm going to label. Chart title. Up here, I'm going to put in natural log of absorbance versus time. And then over here on the y-axis, I now have, again, natural log of absorbance. All right, so the importance of this plot being linear. The natural log relationship for our integrator rate laws for first order, the natural log relationship is a first order relationship for reaction orders if we're looking at integrator rate laws and those equations. And so this plot being linear is basically telling us that our reaction should be a first order reaction for crystal violet. And as a last check for probably 99% of all the reactions we encounter in general chemistry, and even probably to most organic chemistry as well, our reactions are all going to be like 0th, first, or second order with respect to any one reactant. There are some ways that things can get some kind of other fractional weird reaction orders, but it's pretty rare. It's not something that you see all that common. And so really just 0, first, second tend to be the ones we focus on. If none of those plots are linear, now we know to start maybe looking at some of those other a little more odd kind of fractional reaction orders that do sometimes pop up. Now, our last plot, just to kind of go through our process one more time here. We're going to take a look at the 1 over absorbance versus time. And this particular plot's now taking a look at basically is the reaction second order. So if this scatter plot was linear, we'd see a second order reaction. But again, this line, it's not really a line. This looks like a curve, not a straight line. So our reaction is not second order. So based on these 3 plots, I'm going to go ahead and add my chart elements and kind of label everything again here, just to kind of have good habits. So chart title, this we said was 1 over absorbance versus time. Have time down here on my x-axis in seconds. And my y-axis this time was 1 over absorbance. All right. So comparing now my 3 plots, my purpose again of doing all of this is only one of these plots should ever be linear. For any set of data you have, like kinetics-based data of this sort, if you make these plots as far as absorbance versus time, natural log absorbance versus time, 1 over absorbance versus time, or if you use concentrations instead, like concentration versus time, natural log of concentration versus time, and 1 over concentration versus time, all of those, out of those 3 plots, only one of them should be linear. And in this case, we see it's the natural log plot that's linear, so that means it's a first order reaction for that reactant that we're looking at. If the plane absorbance versus time was linear, that would have been 0th order. 1 over absorbance versus time. If that's linear, it's a second order reaction. But in this case, natural log means we should have a first order reaction for our crystal violet that we're looking at. Because it's the crystal violet that's responsible for this absorbance that we see. And the fact that it's changing in a linear fashion here is what's telling us then that we do have a first order relationship for how the crystal violet impacts the rate of our chemical reaction that we're looking at. All right, so that pretty much covers all of the first part of this lab. So I'm going to do this lab kind of like I said in kind of segments for each of them. So for this first part, it's really just all about identifying that reaction order and having these 3 plots generated to kind of verify that. And then in a minute, we're going to start up on our second segment where we're going to take a look at, you know, we have, I think, 5 different experiments worth of data that are all included here. We're going to take a look at calculating rate constants from these plots. We're actually, now that we know a reaction's first order, we're going to be making this plot effectively for all of our 5 experiments and then calculating our rate constant for those reactions from that plot. And we're going to go over kind of how to do that as our next part. All right, so we're going to move into the second part of our kinetics lab as far as kind of going through the analysis portion here for CSE Pub. And for the second part of our lab, now that we've gone through and figured out our reactions first order based on those first 3 plots that we took a look at, what we're going to do is basically make plots of the natural log of absorbance versus time for all of our first few experiments. So to do that, I'm actually going to delete these images of these plots so that they're not kind of in our way here. And what I want to do is I want to actually make a plot of really just time versus natural log of absorbance for all 5 of these experiments. But the way CSE Pub wants you to do it, it wants you to do it with all 5 plots in one single chart, or basically all 5 trend lines and everything all in one chart. And so I want to show you guys how you can kind of go about making something of that sort as well. And what I've done, and you already have this kind of pre-made, this table of data that you have down here, all of this data, these values for experiments 1 through 5 are the natural log of the absorbance values at those time intervals. You will notice experiments 3 through 5, they cut off at 200 seconds instead of going all the way out to 600 seconds like experiments 1 and 2. That's fine. That's not going to cause any problems. That's not a mistake. That's just how those experiments were run. And what I'm going to do if I want all of this in one plot, if I actually set this up so that basically what I want on my x-axis is my first column, I can highlight a whole bunch of columns this way. I'm going to go down so I make sure I get all my data points involved. And I can still just go through my same normal process of insert, chart. I want this XY scatter plot with nothing connected to start. And what I'm going to get is now this plot. All right, I'm going to blow this up here so that you're not looking at just this little tiny chart. Give myself plenty of space to kind of work with here. So now I have all 5 experiments worth of information all on a singular plot. Now, a couple real quick things I do want to kind of highlight here. The blue line here is for experiment 1. The orange one here is actually experiment 2, even though it's ending first. So do keep that in mind as you see some of the values on this plot, and you're putting answers and things into CSE Pub. Because the next thing we're going to do for all of these plots is actually figure out what's the slope of each of these lines. Right? And so there's pretty quick ways to actually figure this out. So let's say we want to look at this first data set. So here, I've right-clicked on one of the data points out of the blue kind of set of data, the dots. And what I want to do is add a trend line. So I'm just going to tell it add a trend line. It added a little, very light blue line going through everything. And I have some trend line options over here that popped up for me. Now, it may be, depending on if you have a different version of Excel, if you're on a PC, you might not be able to do quite the same thing, but you'll probably have something up here as far as chart options that will allow you to add a trend line as well. Or you might actually have a little plus sign just outside your chart that shows up over here, that if you click that plus sign, you'll get some different options for your, where you might be able to add a trend line there as well. So those are kind of the normal places to look for being able to add a trend line. Now that I have my trend line there, these trend line options, like I have this bar here for formatting my trend line that mine auto defaulted came up to this. That might not always happen for everyone else when you add your trend line. In fact, it probably won't. So I'm actually going to get rid of this so I can kind of show people how to get back to it. Here, if I right click on my trend line, I can have an option to format trend line. That's usually probably the easiest way to try and do it. Again, under options, there's usually a way to do it. Or you have the little plus sign over here. That same thing will be like trend line, and it'll have like the trend line. And I'll say like the types, and if you select like other, you'll have a whole bunch of other options, including format trend line that you can pull up. That at some point should end up giving you a window that looks something like this. And the couple things I want to highlight here is I want to display my equation on this chart, and I also want an r squared value. Now, the r squared value, probably not something we necessarily really need. We're not going to be using it for any of the other calculations or anything else we look at in this lab, but it does just give you an idea of how good your fit that trend line is going to be to your data. The closer to 1, the more accurately all of your data fits that trend line. So in this case, like 0.9998 for an r squared value, that means our data is really, really linear. It's a really good fit, which means our data lines up with what we expect for a first order reaction very, very well. Now, the other piece of information we want to get is actually going to be what we call the rate constant. And if you've looked at a first order integrated rate law, that equation is like the natural log of concentration at some point in time is equal to negative kT plus the natural log of the original concentration. Because it's a negative kT, well, t is just the time, that's our x variable, which really means that negative k is the slope of our line here. Well, that means our rate constant k is actually just this number here in front of our x, the slope of our linear trend line, and it's just the positive value, not the negative one, because the negative that's in the integrated rate law. So we really have our k, what we call in this case k effective, is what your experiment is actually calling it. So here's our K effective right here that we're going to be using. And that's really what CSE Pub's asking for, but there's one additional piece to that. And that's that it wants the K effective given to 3 significant digits, but the default for most of your probably Excels are going to be to give 4 decimal places probably on that measurement, which is not actually going to get you 3 significant digits. It's only going to be 2. So we actually want at least 1 more decimal point here. And there's actually some ways that you can actually manipulate that. Oops, my label options here. So notice, and I'll go back, let me get rid of this so I can kind of show people how to get there again. If I'm highlighting the actual box here that has my kind of trend line information in it, I can, again, right click, and I can go format trend line label is what I can do. Again, if that's not an option, a lot of times you can click on this box. If this box is what's highlighted and there's a plus sign out here, then the plus sign will give you options hopefully to format this. And those are probably the 2 easiest ways or most common ways you'll see depending on your versions of Excel. And what I want to do is I just want to take this and over here, if I'm looking at the tab that has all the bars on it, I'm going to have an option to kind of modify the numbers that are showing up here. I'm going to tell it, instead of category general, I'm going to tell it to do a number. And I'm going to tell it the number of decimal places I want. And I'm going to tell it that I actually want 6 decimal places instead of the 4 it actually started out with. And here, after I hit enter, it nicely actually already updated the number of decimal places that it's showing. It might not always automatically update like that. So if you hit 6 and hit enter and it doesn't change, delete this box and then basically re-show the trend line information from like your format trend line options, and it should have the proper number of decimal places at that point in time. Again, just kind of varies in the versions of Excel. Some are a little more finicky than others, but most of the time when you update it here, hopefully it will automatically update your numbers here, and you can see that. And so now if I'm looking here, it's 0.00413. So my K effective for basically experiment 1 is going to be 4.13 times 10 to the minus 3. That would be the number that I'm putting in. Now, the other piece to figure out is going to deal with units. And so for the units part, we actually have to have one other consideration, and that's going to be what is our reaction order? Well, for a first order reaction, your units of your rate constant should always be just 1 over seconds. That's how you're going to get the proper rate constant units in order for your rate, basically for any normal standard rate law, to still come out with units of molarity per second for the rate itself. So all first order reactions, if it's just the first order reaction we're looking at, which in this case we said it's first order for just the crystal violet, which is why we're calling it K effective and not just plain K. This is K effective, it's just really the rate constant with respect to the crystal violet only. Which is why it's first order that we've talked about. And so like, well, first order units on that rate constant that are 1 over seconds. All right, and then what we want to do is for each of these other 5 plots or other 4 experiments besides this first one that we've looked at, basically all 5 experiments in our plot, we just want to go through and do the same things. We want to add trend lines, And once we have trend lines, we want to actually display their equations and our squared values. And unfortunately, one thing that Excel doesn't always do, notice here I had 6 decimal places here. It already didn't do that. So I'm going to go back and fix that and tell it to give me my 6 decimal places on my measurements here so that I have plenty of significant digits in all the things that I'm looking at. So again, blue trend line, this was experiment 1, the orange one was experiment 2. It looks a little out of order just because of where things ended up. We'll get kind of a little bit to more on that in a bit. And then what we're going to take a look at here, our other 3 experiments, same thing. You can right click on any of the data points in them, tell it to add those trend lines. And if I have a line, I can right click the line to do the format trend line if it doesn't pop up this window already. Display my equation and our squared value. And again, I'll have to do the same thing. I'll highlight my box so that I can actually modify the number of decimal places. And eventually at the end of all of this, I can actually properly right click. Oops, that was actually not what I wanted to do. Thought I added a trend line. I think I just tried to format something else. There we go, add trend line. Oh, where'd it go? Here we go. Sorry, it's taking me a second to go through this myself. The versions of Excel I'm used to actually don't automatically pop up this window for me, so I'm actually looking to do extra steps that I don't need to do on this particular version, which is kind of nice. Now I'm going to get my last trend line here, my last equation, and fix my decimal places for it too. And CSE Pub is going to want you to basically go through and enter your K-effective values for all of your 5 experiments, as well as an image of this plot. And probably you're going to want to make and label your axes, so I haven't done that yet on this chart. So same thing, axes titles. You'll want to make sure you add it for both axes, properly labeled, right? For this first one, our y-axis here. For all of them, remember these are all natural log of absorbance because they're all our first order plots. Effectively, it's how we're getting the linear lines. And then for our x-axis, this is our time in seconds still. It's been the same on all of them. And then your chart title, you can title this kind of however you want. I'm still just going to put this as natural law of absorbance versus time, because that's really what this is. It's just and the chart title doesn't have to be one particular thing. You can modify how you want as long as it gives you a good picture of what you're looking at. All right. And if you want to, down here on the actual legend key down here, you can adjust and actually switch. Instead of having like series 1, series 2, you can change your labels here so that you actually have, you can say experiment 1, experiment 2, etc. And remember, the orange is actually experiment 2, blue is experiment 1, which down here will make maybe a little more sense if you have that labeled. You can help remember that as well. But this gets us through pretty much all of the information that it wants for the second part of this experiment. Again, I'm going to kind of cut a clip right here, and then we're going to move into here in a moment what we're going to be looking at for part 3 of the experiment, which is now looking at the other reactant of our reaction, which is going to have us look back at some things on CSE Pub from like the procedure that's described to us there, and do some kind of quick calculations to help us figure out the reaction order for hydroxide, the sodium hydroxide. So that'll be the next part that we get into. All right, so we're going to move into the third part of this particular experiment and kind of describe what it's really going to be asking you to kind of look at and do. And this one's not quite as cut and paste as far as just being able to kind of generate plots with data that's given to us. We actually have to do a little more legwork to kind of figure out what's going on this one. And so for this particular portion of the lab, and really like these kind of parts I've kind of tried to segment things to, if you look on kind of what you have on your CSE Pub assignments and reading, like I have a couple things up here, like this is the Kinetics questions printout. If you go to that link in D2L, you can see this exact PDF. You have your pre-lab questions, and if I scroll down, you basically are going to see all of the data tables, which really are going to be the questions you're going to kind of be asked in the actual post-lab assignment, or kind of what all these data sheets are. So you see like parts 1 and 2, we had like the 3 plots for part 1, and then like what's the reaction order, which you said was first. We have the big graph with all the K-effective values we talked about how we made a second ago, along with the K-effectives for each of those first 5 experiments. along with units then for rate constants as well. And now we want to get into, for the third part of this experiment, we're looking at, what's the reaction order of the hydroxide? Because we've kind of ignored hydroxide in all of this so far. But if you think back to the beginning and kind of why we said that was, it's because we used a huge excess of sodium hydroxide in our reaction. By having a ton of hydroxide, only a little bit of crystal violet, the hydroxide concentration was pretty much effectively constant throughout the whole thing, and that would have then an influence on how our reaction proceeded. Now, what we're going to do is, if we look at the reading for the actual lab, and this is, I'll scroll to the top of it so you can see it. This is the reading for the kinetics lab. If you open it up in either through CSE Pub or again your D2L link for the reading for the lab assignment and the procedure. If you go all the way and kind of work your way down towards the bottom, past the pre-lab video if it's still listed there, you're eventually going to see the procedure section. And this is what we actually want to pay close attention to, because it actually tells us for each experiment what all the exact details were. And so, for instance, experiment 1, it's giving us here, how we set up that spectrophotometer that I showed an image of already at the kind of very beginning. And it also gives us the specific details here in this particular portion. It's telling us that to do the reaction, 5 milliliters of 2.1 to the minus 5 molar crystal violet were placed in a test tube, and then 1 milliliter of 0.10 molar sodium hydroxide was added to that test tube. And everything was thoroughly mixed, and they did the reaction, and then a small aliquot, which basically just means a small portion of the contents of the test tube were placed in one of those cuvettes that we had seen earlier, and we measured the absorption every 20 seconds for a period of 600 seconds. So it gives us kind of a general experimental summary of what was done. And we also note for experiment 2, it's the same concentration of crystal violet and the same volume of crystal violet, same volume of hydroxide, but the hydroxide concentration was different. This is why plots 1 and 2, when you actually looked at your plots for all those K effective values, why they kind of crisscrossed was actually because they had different sodium hydroxide concentrations involved in them. The bigger concentration of hydroxide in experiment 1 made the crystal violet concentration effectively react faster and disappear faster is kind of the overall effect that we saw, which means that likely sodium hydroxide is not a zeroth order reactant. But if we want to find out its actual reaction order, we do still have to do a little bit of legwork to try and figure that out. And so how that's going to work is actually involving an equation, kind of a relationship that we basically kind of created for ourselves a little bit earlier on in the lab. And I'm going to actually scroll back up to where that really first came up. And that's kind of this equation right here for K effective. So I'm going to show you kind of some things here by hand that I'm going to write out about how we're going to go about answering the questions that CSE Pub wants you to be able to answer for this third part of the experiment. And one of the starting points is going to be the fact that K effective, the way we've defined it, is that K effective, based on this equation that you see right here, K effective is the actual rate constant times the hydroxide concentration raised to its reaction order. So the actual rate constant, we'll call it K. If I can, let me write a little bit cleaner here. The actual rate constant K, it should be lowercase if I was a little more effective at writing this, times our concentration of hydroxide to its reaction order N. So our goal is we really want to find N right now. And how we can go about doing that is very similar to how we find reaction orders for method of initial rates type problems that you've probably hopefully seen in lecture. And it's the fact that for experiments 1 and 2, we actually have information that tells us, we've already found K effective for basically experiment 1 and experiment 2. We know the concentrations of hydroxide in experiments 1 and 2. And the whole rate constant for experiments 1 and 2 should actually be the same. So what we're able to do is if we take K effective 1 and basically rate constant 1 and the hydroxide concentration for experiment 1, and we divide all of that by K effective 2 being equal to our rate constant 2, which remember K1 and K2 really are equal here. So those two are effectively going to cancel out of this in a second. And then we have the hydroxide concentration for experiment 2, also to that same reaction order, because the reaction order shouldn't change between experiments. Well, what we're left with here is we get these ratios of K effective 1 over K effective 2. And I apologize, these really should be lowercase k's. Lowercase k's are rate constants. As you get on to the next chapter, you'll see that capital K's are actually equilibrium constants. That's why I'm trying to be a little careful in my notation here to hopefully make that obvious as I write these out. But that ratio is going to be related to the hydroxide concentration for experiment 1 to some power over the hydroxide concentration of experiment 2 to that same power. But I can actually rewrite that a little bit if I get rid of that power there and actually just put all of this ratio in parentheses, then raised to some power. So what I effectively have here is I have K effective 1 and 2 that I already found earlier in kind of our data analysis part of this. And I can find these concentrations by doing a little bit of M1V1 equals M2V2 with the experimental information that I was given in my reading on CSE Pub. So if I look at my reaction descriptions again here, they're telling us, we had 5 milliliters of 2.1 to the minus 5 molar crystal violet, and then 1 milliliter of either the 0.1 or the 0.05 molar hydroxide. What I want to do is basically do a quick M1V1 equals M2V2 to figure out what is the concentration of hydroxide when all of this was mixed together. Because we are effectively doing a small dilution where we have 1 milliliter of the hydroxide solution, and then we're adding 5 milliliters of, in fact, you can almost think of it as just water in terms of the hydroxide concentration, because we're not adding any more hydroxide with those 5 milliliters. So we started with 1 milliliter at one concentration. We want to know what's the final concentration when we get to our final total volume of 6 milliliters when we mix those two solutions. And so we can just do a quick M1 V1 equals M2 V2 to find that concentration, right? And so just kind of very quickly here, I can kind of write that out. I can show like M1 V1 equals M2 V2, right? That's our typical equation for any kind of dilution. And what I can show here is that our initial concentration of the hydroxide, let's say it's for experiment 1, we said was 0.100 molar times a volume of 1 milliliter needs to equal M2, which is what I'm looking for, times the total volume that we're ending at, which is 6 milliliters. Right, so if I can just divide both sides by 6 here, scroll that down just a touch. Dividing both sides by 6, I see that I get a final concentration. There should be about 0.167. Let me make sure I'm going to have my decimal points right here. That is not 0.167, I think it's 0.0167. So it's going to be important here. 0.0167 molar. Right, that should be the actual concentration of my hydroxide at the start of my reaction. That's important because remember, it's those initial concentrations that are going to have impacts on things like initial rates for our reactions when we look at them and talk about them. And so this is going to be for experiment 1. So now I have my hydroxide concentration for experiment 1 that I'm going to actually be able to kind of come up and plug into the equation I had before. But I also need the hydroxide concentration for experiment 2, so I'm going to do the same thing again. The only thing that was different was the concentration was half as much, right? So it was 0.05. Oops, I can get my Apple Pen to respond here. 0.05 molar times the 1 milliliter over the 6 milliliters should be the final concentration, which I believe this comes out to like 0.00833 molar. And that's for experiment 2 that I can now plug into this equation as well. And then what I'm going to do for my K effective 1 and K effective 2, if I go back to the Excel data that we've generated previously, so I have an Excel plot up here that I can hopefully make my way back to. So here's our Excel plot. Remember the blue is experiment 1, so 0.00413. So K effective 1 was 0.00413. K effective 2 is the orange one that's actually above it, 0.00246. I now basically have, and what I've done is I actually wrote those values into my calculations here. So I have those two numbers. I just found these two numbers. I can plug all of this in and hopefully solve for this n value. And the thing to remember about this equation and just n in general, n should be equal to 0, whoops, if I can write hopefully a little more legibly, 0, 1, or 2. Right, those are kind of our main possibilities. We don't expect something different than that. It is possible you can sometimes get like a half or 3/2, but it's pretty rare that we see something like that. And so we're expecting one of those two numbers. And what we're going to do now is just calculate these ratios. And so if I actually take, and I'm going to scroll down here, if I take 0.00413 divided by 0.00, what was it, 246, that's going to equal 0.0167 divided by 0.00833 to some power n. And if I calculate these numbers, I'm going to get, let's see, on the right side's easy. This is going to be pretty much exactly 2 to some power. Has to equal 0.00413 divided by 0.00246, which I get as about 1.68. So if I want to think, all right, 2 to what power gives me 1.68, it's not going to be exactly 1, right? In here, if we actually solve for this n using logarithms, it's probably going to be somewhere like maybe around like 0.7 something. But we do want and expect a whole number here. The only other possibility besides maybe getting n as a whole number is n being like 1/2. But if that was the case, 2 to the 1/2, this would be like the square root of 2 would be about 1.41. It's not really that either. So we actually are going to take a little bit of liberty here and kind of rounding things and say that n is approximately 1 from this result. Like 2 to the first power should normally be 2. We're getting 1.68. It's not exactly 2, but it's also, we're not getting 1 and we're not getting 4. It's closer to 2. So we do expect this to be a first order relationship for the hydroxide. In a perfect world, we'd probably have additional experiments that we could also compare to try and get better confirmation. But this is the data that we have that we're going to work with. So we're going to basically use this, again, assume that n is really close to 1 is kind of our big takeaway from this. So if you're looking at like your, the things that CSC Pub is going to ask you for, and wants your hydroxide concentrations that we just found and the order of the reaction. And then the last thing it's going to want is K, the actual value of K. And if I want to find K, what I can do is I can go back to kind of these calculations I've been doing, and instead of the whole fraction that I made up here, I can just take the first part. Right? I can say K effective 1 is equal to K times my hydroxide concentration for experiment 1 to the n power, where we now said n is 1. And I have n is 1, I have this concentration, I have K effective. All I have to do now is solve for that K. And so that'll be what I show for this last part here to get our rate constant. And then we'll talk about the units that rate constant should have. So K effective for experiment 1 was that 0.00413. And if we think about that thing's units, we said earlier K effective had units of 1/seconds. We can actually pay attention to our units here and it will help us. Is going to be equal to K times, this is my hydroxide concentration, is the next part I'm writing, for experiment 1, which was the 0.0167 molar, to the first power. And so I'm solving for this K. So if I solve for that K is 0.00431, or 413, 1/seconds for the units, divided by 0.0167 molar. And now I can go ahead and just calculate that to get a number. So 0.00413, I'm just going to calculate this real fast, by 0.0167. We get 0.247 roughly. So 0.247. And for the units, notice I have 1/seconds divided by molarity. That means molarity to the -1, seconds to the -1 for my overall units, which should look like a familiar unit. That's the unit you get for a second order reaction typically. And this is going to be an overall second order reaction because crystal violet is a first order reactant. That's what we found in the very first part of the experiment by the fact that the natural log plot was the linear one. And we just showed with the numbers here that hydroxide is also a first order reactant from what we think. And so if we have two first order reactants, the overall reaction is second order. Those are the typical rate constant units for a second order reaction. So those are the units that we would expect. All right, so that gets us through kind of all of the parts, or kind of the third part of the experiment. We have one more part that we'll take a look at in a moment that's going to deal with kind of temperature effects on reaction rate. And that'll be kind of the last little bit that we'll talk about for our kinetics lab. All right, so for the last part of this experiment, the fourth part, If you look at your kind of data sheet and what CSC Pub's going to kind of be asking you about, our goal is to find the activation energy of our reaction that we've been looking at between that sodium hydroxide and the crystal violet dye. So the information that we really need here and kind of what we need in order to kind of look more at the activation energy is really going to involve temperature. So remember, we had 5 experiments of data that we saw previously that we were using, but we've really only looked at kind of the first 2 experiments a little bit more in depth in terms of how they were done. If you actually look back at kind of your CSC Pub reading for the other experiments, experiments 3 through 5 are done the exact same way as experiment 1. The only difference is the temperature. Experiment 1 was done at 25 degrees. Experiment 3 was started at 35, 4 at 45, and 5 at 55 were their starting temperatures. Now, you might notice those are not the actual temperatures that were given that you'll actually see here in a moment in our Excel data sheet. And so I'll pull up our Excel sheet. If you scroll down from your starting Excel, from what it looks like initially, just scrolling down, you're going to see some data down here. And so here is some temperatures, right, in degrees Celsius. These are the average temperature for experiments 1 through 5, or actually experiments 1, 3, 4, and 5. We take out experiment 2 here because it had a different concentration of hydroxide, so we didn't want its K effective being kind of used the same way. But what we're actually able to do here is we're going to use the Arrhenius equation. And to talk about the Arrhenius equation for just a second, and then I'll come back to the Excel spreadsheet. Oops, not this one. I'll take a look at this. Our Arrhenius equation, kind of its most general form, is that our rate constant is equal to A times E to the negative EA over RT. Right? That's kind of our general form of the Arrhenius equation. Now, if we want to get temperature a little more accessible so it's not in like the exponent of something, we can take the natural log of both sides of this equation. And that'll give us the natural log of our rate constant should then be equal to basically negative EA over R times 1 over the temperature plus the natural log of A is kind of how that will all break down. And so now what I have here, I actually have an equation of the form of y equals mx plus b, right? Natural log of A is effectively my b, 1 over t is now my x value, and negative EA over R is going to be my slope, and the natural log of K would be my y-axis value. So what I actually want to do is I want to make a plot where I plot 1 over my temperature, and I want to put that on my x-axis, and then I want to take the natural log of my rate constant, and I will be particular just so there's not too much confusion. We're going to use K effectives for us on this because we already have those calculated. So we're going to use K effectives for experiments 1, 3, 4, and 5 that we found earlier. And what we're going to do is we're going to put those values into our spreadsheet and make a quick plot. And if we make a plot, it should be linear. We can make a trend line. We can get a slope. And from the slope, now, if we know the slope of our trend line should be the negative activation energy over R, well, if we just multiply our slope by negative R, that should give us the activation energy. And it should be a very big positive value when we get to the end of it. So I'm going to go to that part then. So here, what you'll already see probably farther down in that bottom left of your Excel spreadsheet that you started with, these are the values they gave you to start out with. They already gave you temperatures in degrees Celsius. They already converted them to Kelvin even for you. Because it is important to note, anytime we use an actual temperature, it does have to be in Kelvin to be used properly. And for the equation and the calculation. And so the other thing we will do here, we will make these 1 over the temperature, right? So we can do kind of what we did before. If you put an equal sign, Excel will know it's a calculation. We'll say 1 divided by, then we'll highlight, oops, didn't like what I did there, not sure why. 1 divided by, there it goes, our other cell. And then if I come over here, I can double click in the bottom right corner with the black crosshair, and now I'll get those values calculated for all of these. Now there's my 1 over temperature that I want on my x-axis. Now I want my K effective values, which we already talked about are going to have units of 1 over seconds. For the general units, here we see this is Kelvin, basically inverse Kelvin on units. And my K effective values are basically what we had in this plot. So if I scroll down, I can find all my K effectives. K effective 1, this was the 0.00413. K effective 3, that'll be this one, was 0.00583. K effective 4 right here, 0.00823. And notice all of them are getting slightly bigger. This should make sense because all of these our temperature was going up. As temperature goes up, reaction rate should get faster because the rate constants will get a little bit bigger as well. And our last one here, rate constant was actually 0.0105, it looks like. So there's our 4 K effective values. Now, what we want for our plot, though, is not just K effective. We actually also want it to be natural log of K effective. So what I'm going to do here real quick, so I kind of scroll over and give myself some space. I want to take my, I'm going to take these values. Well, actually, at this point, I'm just going to go ahead and actually insert a column here. Tell this to insert, so I get a column. And what I want is I want this to be the natural log of K effective. So natural log of K effective. And I'm grouping it this way just so I can have my values right next to each other. But now what I can say is I can say equals, I want to take the natural log of that column, basically that cell, hit enter, again click it, double click to get my natural log, my other values. And these natural logs, they should be negative. We're taking the natural log of a number less than 1. We are going to get negative K effect, or natural log for K effectives. That's perfectly fine. But these are the data points I actually want to be able to highlight to make my plot, which is why I kind of organize things that way. So now if I make my scatter plot, here's my plot. Again, I can add my chart options that I want with my axes titles. And I'll let you guys fill those ones out this time. I'm not going to kind of fill them in here. But the last thing I want to do, I want to add a trend line, right? So if I click one of my data points, I can say add a trend line. I'm already getting my options over here, display R squared, display equation on my chart. And it's this equation I really care about the most, right? Because what I'm looking for is my activation energy. And we said that the slope of this line is negative EA over R. So and I already have a pretty negative large value for the slope. But when I multiply this by R, the ideal gas constant, or really I need to multiply by negative R, I should get a very large positive number. Because the R in this particular equation, that Arrhenius equation, is going to be the 8.314 like joules per mole Kelvin version. Because we want joules in the units. Activation energy is going to have units typically of joules per mole or kilojoules per mole. And so we are going to get a very large value for this activation energy when you find it. If I remember right, it's like 20-something thousand when you get to the final answer. So that's pretty much all we're doing for that last part. Using an Arrhenius equation, making this plot kind of based on that, getting that slope to help us find our activation energy, which should be a big positive value at the end. And again, the other thing I was just kind of highlighting here, the fact that, again, should hopefully make sense. Reactions get faster as they get hotter. There's more collisions happening more often with more energy, so the reaction should happen more often, which will make our rate constants bigger. It's kind of the trend we're seeing here. And we can get our activation energy based on kind of the relationship of how much the reaction gets faster as we raise temperature. Which is kind of a neat thing that we can do and a useful thing that we can do because knowing activation energy also lets us know a lot more about the reaction that's taking place and perhaps ways that we can either improve or alter that reaction in the way it's happening as far as kind of like potential like down the road applications for things. So that pretty much covers, I think, all of the major kind of data analysis and content that I want to get to for this lab. I thank you for kind of bearing with me through all of this video. I know this is definitely one of the longer videos. And there's a lot that we've kind of gone over here. Hopefully, though, this has been kind of informative to really kind of familiarize yourself with Excel, for one thing, on top of taking a kind of a little more in-depth look at kind of applications of kinetics, how kinetics can be used. And if you have questions, please reach out to your instructor. You can always reach out to myself, Dr. Meyer, as well, to help with any issues you run into as you're trying to kind of do these calculations yourself and enter things in CSE Pub. And then I will see you next time. Have a good one.